Today I will be demonstrating an experiment with regard to optics. This is one of the experiments you require in your 12th grade practicals. So what you need to know about the optic experiment is what are the different apparatus we will be using it and how we will find the readings. So first I'll just show you what are the different parts in this particular experiment we'll be using it. Okay, so here you will see that we have this particular apparatus called as optical bench. This is optical bench. Then this particular thing is called as lens holder. It will hold the lens. These are the screws given to us to remove the lens and to adjust the height of the lens. Now this particular part of the optical bench is the pin holder and this is pin. So if you just tighten this screw or you untighten it, you can adjust the height of the pin. Same way we have one more pin over here. Remove the pin and adjust the height of the pin using this particular screw. Now very important thing is that these pins which we are using, they are made up of metal and they are pointed, so you need to be very careful and very cautious while doing this or performing the experiment. Main part, this is the screen we will be using for background purpose. There is the calibration on this particular rod. That's like a scale, a meter scale. Starts from 0 from one point to 100 up to other point. This will be acting as the object pin for us. So this is the object, this is the lens. We will be getting image somewhere on this side. Okay, so we will be adjusting this particular pin to get the exact image. How we will get the image, I'll let you know. But since this is my lens and this is the object pin, distance between the lens and the object pin is called as object distance. We take this as U. This is my image pin. The distance between the image pin and the convex lens will be my image distance. We take this as V. Basic thing and 3 steps before you start this particular experiment. One thing is you need to look at the given lens properly. This is the convex lens because the lens is thick at the center and at the periphery it's thin. So this is my convex lens. Second thing, always wipe the lens from both the surfaces with the clean cloth so that there shouldn't be any markings or fingerprints on this. Third thing, you have to find the rough focal length of the given lens always first. So I'll show you how you will find the rough focal length of this given lens. Pause. So to find the rough focal length, you need a scale, lens, a screen and an object. For time being we are taking this CFL bulb as the object for us. So this is object. I keep the scale here and I adjust the lens in such a way that I should get the image of this particular CFL. You can see here how I am getting the image of this particular CFL. I need a clear image. So this is blur image, but if you look at this is the clear image what we are getting it. So you have to adjust the lens in such a way that you get the clear image. Okay. So you can see you get blur image at this end, you get blur image over here. So there has to be in between where you get the clear image. Can you see this? This is the clear image of the CFL. We want such image. After that you will measure the distance between the image and the lens which is on the scale, and for me it is giving 10 centimeter. So this is how you get the rough focal length of a given lens. Next part is balancing of optical bench. How do we balance the optical bench? We have screws at the end of the optical bench. Can you see this? These 4 screws. We have to adjust these 4 screws in such a way that the whole optical bench should be completely horizontal. So for that we have something called as spirit level. You can see inside this liquid there is a small bubble. This we will be going to place at all the 2 ends of this, and if this bubble is not exactly in between of these 2 black lines, that means we need to adjust the screws over here. But since if you look at the given bubble which is exactly not at the center but somewhere here to the right, but this is okay. I move this optical bench on the other side, and again I try to see, is this bubble at the center? You can see that it's a little bit towards the right, but for this it's okay. This is how you balance the optical bench. If this particular bubble is not in the center, you will adjust these screws which are given at the ends. Try to bring the bubble in the center of a spirit level. Second thing, first finding the rough focal length. Second, balancing the optical bench. Third part, the pins which we are using here, that is the image pin and the object pin, plus the lens which we will be using, they all should be at equal height. I'll just place the lens and I'll show you that how you can adjust the given lens and the pin all at the same height. So what I can do is that I need this point of the image pin at the center, so I just keep this scale and I see that yeah, this is horizontal and this is at the center. Same thing I do it here also, and I check that if it is not at the center, that is the optical center, then I raise the height of the pin so that 2 pins and the optical center, they all have to be in the same line. So 3 things very basic you need to know about optical experiments. First, finding rough focal length. Second, balancing the optical bench. Third, arranging the pins at the optical center. 3 things. How to perform the experiment? We'll move ahead now. So how are we proceeding ahead in the experiment? This particular experiment, what we'll be doing is finding the focal length of a given lens by UV method. U is object distance, V is image distance. We'll be using UV method to find the focal length of the lens. So let's say that this is my object distance. I take this object distance, let's say as 20 centimeter. We have a scale on this, and I take this. You may not be able to see this, but yes, while performing the experiment you can see this. I have adjusted this at 20 centimeter. You can see this, it's 20 centimeter. So my lens is at 20 centimeter. Object pin is at 0 centimeter. You can see this, it's 0 centimeter. So object distance is 20 centimeter. Next part is very important. We'll place the screen, that's to no background, any effect of light on this particular object pin. We have to adjust this image pin in such a way that it should be under a non-parallax position. I will tell you how will you adjust this at the non-parallax position. So you have to stand somewhere at the end. This is my image pin. When you look through the lens and you look at the object pin, obviously this is convex lens, this will give us the inverted image. So I will see inverted image on the other side. I will adjust this image pin with the image what we see from there, and my object pin and image pin, they both should move together point to point. So I would like to show you one such position where you have to move your head towards left and right in such a way that both the pins should move together. So let's say I have adjusted, okay, and in this particular adjustment my object pin, which gives me the inverted image, and my image, they both are moving together. So this is how you will get the image. Yeah, so finally you will see the image something like this when you move your head to left and right, and this is the non-parallax position. I will just show you that when you move your head towards left, like you are moving your head towards left by closing one eye, you can see that how the object pin and image pin, they both are moving together. Can you see this? This is called as non-parallax position. Again, I am taking my eye towards left and I am taking my eye towards right. So basically this is the non-parallax position, and for every reading of optics you need to find such kind of position. I'll just show you one more reading where it's under a parallax. One second. Okay, so now observe this. You will see that your object pin and the image pin, they both are not moving together. Can you see this? Okay, so this means that this is under a parallax. I'll show you one more such image. One second. So if you look at this particular reading also, you will see that the object pin and image pin, they both are not moving together. Look at this. They should move tip to tip together with each other. So this is again a parallax position. Okay, look at this. They are separated from each other. We don't want such readings to happen. We want the non-parallax position which I showed you earlier. Okay, so once you know how to remove the parallax, that's the non-parallax position which I have showed you just now, you have to measure this image distance. U was 20 centimeter. If we measure this V, you will get some value over here. So this may be somewhere 40 or something like that, or whatever is the reading. You measure this distance, which will give you the image distance. Okay, so after explanation about that particular experiment, which is UV method, what we did, you will see that this particular diagram, what you see on the screen, what are the values of U and V. So if you look at this particular diagram, from optical center up to here, which is object, will be my U. So this distance is U, and the distance from image, what we got inverted image, it's already shown here. Can you see that this is V? So for different values of U, we have to find different values of V. So how are we doing it? That I have already explained you. Now what I'm going to show you that what is the different calculations you have to do here and what graph you have to draw. Actually, for this particular table, you have to draw each time one graph. So can you see this? It's mentioned over here. Find the value of repeat. Plot the graph of V corresponding to U. This is my experiment number 1. Then for the second experiment, everything will remain the same, but instead of plot of graph of V corresponding to U, we will change only the graph. I'll tell you which graph you have to draw. That will be my experiment number 2. Experiment number 3, Again, everything remains the same. My observation table, everything as it is. And you will draw the third graph. So 3 experiments, observation table remains the same. And for same observation table, you will draw 3 different graphs, 3 different experiments. Okay. So if we look into here, what values did we tried last time? I'm just giving you that values. So basically we let's say it's observation number 1, lens. You should read properly. It says position of. So wherever the lens or the object pin or image needle was placed, we have to write that over here. So my object pin throughout the experiment was at 0 centimeter only. So here for all the readings, I will write this as 0 because we haven't changed it. Okay, the position of the object pin. Whereas for the first reading, we kept the lens at 20, whatever the reading we got. Same thing you can do it for 30 if they have asked. Then if the lens is at 30 centimeter, by doing that particular experiment, we got image needle at 45.5. So I get this value as 45.5 centimeter. So object distance is the distance between the lens and the object pin. So if you look at the distance between the object pin here and the lens, okay. So here you will see this 45.5 object distance I will get here. I will write that value of object distance here. The object distance is the distance between the lens and the object pin, which I get this as 30 centimeter. If I solve this, I get this value as 15.5. This is my image distance. Image distance is the distance between the image needle and the lens. So 45.5 minus 30 will give you this. And we have to substitute these values of u, v here and get the value of f. You have to show some calculation here and then you can write f here also, or some calculation somewhere in the journal to show that how you are getting this value as of f. By calculation we get this in centimeter unit, and this value what we get is 10.21. Similar way we do second, third, fourth and fifth reading for different distances or the position of the lens. Lens first place what 30, next will be let's say 35, then it's 40, then it's 45, 50. Okay, and I suggest take one more reading on a safer side as 55. So when we did this experiment, we got this values as this distance, that is the position of the image needle will be at 50, this will be at 54. This readings what I got is the approximated readings. You can do this experiment and you can get this a little bit variation in the readings. So it's 67.8 here. If I solve and I fill the column for object distance, my object distance here I get this as 35. I get this as 40, 45, 50, and final reading will be my 55. So image distance here what I will get is 15, 14, 13.4, 13.5 and 12.8. When I substitute the values of u, v in this particular formula, we get this as 10.50, 10.37. I get 10.32. Here also I get 10.32. And this is 10.38. This when you do the calculation, this is not 32. I think you get this as 10.62. So this value you get as 10.62. Okay, then you have to find the focal length of the convex lens is dash centimeter. So when they say focal length of the convex lens is dash centimeter, they mean to say the mean of this all values. So when you find the mean of all these values, that is 10.21 plus this, you know very well how to find the mean, divided by 6, you get the answer as 10.4 centimeter. And when we found the rough focal length, that you should write in your journal up here, that rough focal length, what we got when we did in the experiment over there. So rough focal length we got there as 10.2 centimeter something. So that value of rough focal length and what you get the mean value of this should be the nearly same. So if I write this value and my rough focal length up and here, they should be very close to each other, and this is the result. Now, how do we get this formula as f equals to uv upon u plus v? I'll tell you that. If we have a formula f, which is 1 by f equals to 1 by v minus 1 by u, and if I use the Cartesian sign convention, looking at the diagram which is given over here, what are the different values of v and u we get? So if you look at this end, what value do you get for u and v? You look at this distance, which is v. We are measuring this distance in the direction of the incident ray. That is, this is my incident ray. So direction of measuring from the optical center is like this. So my v will be in plus, and when we measure u, we are measuring it in the opposite direction. So this is minus u. When I substitute this in the Cartesian, when we substitute this in the lens maker's formula, then how do we get this as the equation? How this gets transformed? It's 1 by f equals 1 by v minus of minus u. Therefore, it is 1 by f equals to 1 by v plus 1 by u. I simplify this ahead, I get that 1 by f equals to u plus v upon uv. And when I find the reciprocal of this, I get this particular equation. Can you see this? And get this equation which is in front of you. And the unit used is centimeter. Now, drawing the graph, you will plot all these points and you will draw the graph. And if you look at what instruction is given over there, my UV graph should be how it should be. My U versus V graph should be a curve. That means you plot V corresponding to U, how you should get the graph. Okay, I'll just try to show you the graph. So how do we draw the graph in this case here? Okay, now what you have to draw for the graph is